So like in R3, planes are an embedded hypersurface, for example. So here's a simple proposition. I won't write too many propositions here today, but here's one I'll write. M, a smooth manifold, the embedded submanifolds of the codimension 0, what are they? Are exactly, what's that? Yeah, they're the open submanifolds. And what are the open submanifolds? Open submanifolds that's just a fancy talk for saying take any open subset of the manifold and view it as a manifold by the natural restriction of the atlas which pertains to that open set. Just that. His next proposition says basically that if you have a smooth embedding from a manifold N to a manifold M, and you look at the image of F under N, then with respect to the subspace topology, S is a topological manifold and has a unique smooth structure, making it into an embedded submanifold M with the property that F is a diffeomorphism onto its image. I would say this is not particularly surprising. The condition of the smooth embedding means that like the differential is full rank. Okay, so like if you restrict the codomain of a map to just be the image, it's essentially like surjective. So you've got a surjective map with a full rank differential. So yeah, that's going to be a diffeomorphism. Anyway, I'm gonna move on. All right, so proposition 5.3. You've got M and M smooth manifolds. All right, M cross P is called this is this is a subset of M cross N, right? Right. This is a what this is called is a slice. This is a slice of the product manifold, slice of M cross N. It's a slice. Slice of the product manifold. It's an embedded submanifold. What do you think it's diffeomorphic to? What do you think what do you think the slice of M at P is diffeomorphic to? Not TPM. Come on, guys. Diffeomorphic to M. Yes. There you go. Thank you. Another proposition, and this one's probably actually pretty useful. Proposition 5.4. Again, you got a smooth M manifold without boundary and a smooth N manifold without boundary. And we've got a function F which goes from some open subset of M to N, a smooth map. Okay. In that context, we can write this thing here. Gamma, capital gamma of F is a subset of the Cartesian product of M and N. All right. In particular, gamma of F is the graph of F. The graph of F is the set x comma y in M cross N in the Cartesian, the product manifold, such that, guess what? X is an element of the domain of F, U, and what do you think we can say about Y? Yeah, well, f of, right idea, but f of x, right?
Yeah, I thought you meant L.
Oh, it's fine. So yeah, that's the graph. And what can we say about the graph? It is a submanifold. What's its dimension? So this is a embedded m-dimensional submanifold. Of the product manifold. Okay, that's pretty nice. And the proof of proposition 4.1, really, all you do is you just study this map. You study the map gamma sub f of x equal to x comma f of x, right? And you can study that mapping, and it's not too hard to show that that in fact is a smooth immersion, right? If you can kind of think about the differential of this map, x is essentially the identity map on the m-dimensional tangent. So like that's automatically going to get you rank M, I think. So anyway, you can argue that's a smooth immersion, which makes this a embedded m-dimensional submanifold. If you cross all your I's and dot all your tittles, all that good stuff for the topology here. All right. Let's see here. He says, for some purposes, being an embedded submanifold is not quite strong enough condition. An embedded submanifold S is said to be properly embedded. So properly embedded means that S, which embeds S into M, is a proper map. What is a proper map? Right. Let's see here. Oh man, well, what good is it if I look it up and I don't write it down? I forget what proper map means off the top of my head. It is discussed in rats. It's not discussed here. It's a topological condition, if I remember right. Let's see here. I don't have the book, so I can't just, oh, you have the book, you cheat. What does it say?
Where?
What's the definition of proper map? It's in Appendix A, I think.
Appendix A? I flipped to a random page in the back, and we saw it at a
Crazy integral.
Yeah.
Oh, that's why you're laughing.
It had like...
So A, I think it's defined in Appendix A. It should be around theorem A57.
A57, so go
A little bit back. The definition ought to be close to proper. What's the definition of proper? We may never find out.
It says properness right here.
Okay.
Should have happened before that, right?
Yeah.
But the problem is these all say proper.
All right, fine. Oh, wait a minute. I'm going to move on. All right, so moving on. All right, so, whoa. Anyway, For embedded submanifolds, you can find something called a slice chart. And so a slice chart, basically what it does is it makes the submanifold look like there's a chart where the points in the submanifold are obtained by setting the rest of the coordinates you're not using equal to a constant. So like an example of a slice chart that would be easy for me to talk about here in 3 seconds is, you know, how about this? Like a submanifold. Here's a submanifold. Z equals to Z naught, right? So like the slice chart on that, if I take an x of a point on this thing right here, that point, right? It's equal to, you know, P1, P2, and Z naught. That's a slice chart. It has the last coordinates in the chart are just fixed to a constant. So like the stupidest example is something like this, but it's a more general idea. And theorem 5.8 says that if you have a smooth n manifold and you have a embedded k-dimensional submanifold, then S satisfies the and if S satisfies the local k-slice condition, which is to say that you make your charts look like, yep.
Is like x equals y, is that a slice?
Is x equals to y a slice?
It'd be like x, x, z.
So you're saying this is our submanifold?
Yep. Oh, x, x.
Oh yeah, XX. Let's see here. Then I would have to find a slice chart on the whole manifold. So like, I'll use phi for a second here. Phi of, you know, let's say AB, because I'm not thinking of another letter at the moment. All right. So it'd probably be something like, I guess I could do something like, yeah, A maybe, and then simplest thing, B minus A. So like if I take a point in S, right, like phi restricted to S, right? For A, B, and S, it's just A. So that's the zero slice with respect to that coordinate system. I could have made it equal to 1 if I was more, I don't know, something like that.
So it's not just that like you hold a point.
Well, the point of this is much like the rank theorem said you can take a complicated, funky, nonlinear function from m to n and choose coordinate charts, which makes the manhandle the formula so that it becomes essentially the identity transformation at the coordinate representation level, right? This is a similar idea, saying that you can pick charts that makes it look like the submanifold is just like a silly, you know, slice, Cartesian slice.
So in 3 dimensions, can you say x of p equals p1, comma p1, comma p2? Is that valid?
For what?
In so like instead of p1, p2, z naught, can you say p1, comma p1, comma p2?
Not for this one, because my like the S I'm thinking of here is two-dimensional. P1 Z naught. Well, I don't think that would.
P1, P1, P2.
P1 P2.
Never mind.
I don't know. I don't know. But anyway, the long and short of it here is that S is a topological manifold of dimension k, and it has a smooth structure, making it into a k-dimensional submanifold. Anyway, what this theorem says is that if you can find slice charts for your submanifold, it means it's an embedded submanifold, in short. Kind of like the corollary to the rank theorem we talked about earlier. All right, so theorem 5.11 is interesting. It says if you've got an m-dimensional smooth manifold with boundary, then the subspace boundary of M is actually an n-1 dimensional manifold. And in fact, it has a smooth structure such that it's a properly embedded submanifold of M. So the boundary manifold is a submanifold. So that's nice. It's a nice result. Theorem 5.12 we'll actually use for examples in the Lee stuff. So let me write that out here. So theorem 5.12 says this: if you have a mapping phi from M to N, all right, a smooth map, with constant rank R, then each level set of phi is a properly embedded submanifold of codimension R and M. Let me write that out. So then, let me just show you what it is actually. So what we're talking about is, let me write it this way. Phi inverse of, let's say, Q, right? So what that would be is P and M such that phi of P is equal to Q. That's a level set. So a level set is like the solution set of an equation. So like all of the P and M which solve that, all right? Then what this says is that that is a properly embedded submanifold of codimension R and M. What's that mean, codimension R? Codimension R implies dimension of the level set is what? What's that? The dimension of M, right? Minus R. Codimension R. So like a plane in 3 dimensions has codimension 1. A line in 3 dimensions has codimension 2, for instance. And then he goes on to talk about so-called regular points and critical points of these maps, and describes the regular set theorem, which says that every regular level set of a smooth map between smooth manifolds is a properly embedded submanifold whose codimension is equal to the dimension of the codomain. And example 515 applies this to to spheres. If you look at the mapping, I'll end with this, guys. So F goes from Rn plus 1 to R, defined by f of x equals to the length of x squared, all right? You can prove that that is a smooth map of constant rank R. Smooth map of constant rank R. Well, I shouldn't say that. Oh, the thing was, if you read the section more carefully, he goes on to explain, even if it doesn't have constant rank on the totality of the domain, as long as it has constant rank on the inverse image of the set, that suffices to give the criteria that you need. So it's a little bit easier than just having to have constant rank anywhere. It suffices to have constant rank on the inverse image that you're solving. So like here, the sphere, the n sphere, is what? So he calculates the differential here. The differential at x of v is just equal to 2 times the sum over xi vi. So that's like there's a formula there for the differential of this map. He says that that's surjective everywhere except at the origin. And how does that give you a sphere? Like do you see the sphere here? So like Sn is what? So we're talking about x and n and Rn plus 1, right? Such that what? Such that the length of x squared, or just the length of x is equal to 1, right? But we could put square there. So this would literally be the inverse image of 1. So
Could be the end sphere.
so that means, yeah, right. So the codimension is 1. So your n plus 1, codimension 1, means you're n dimensional. So this, properly put in place, proves that the n sphere is in fact a n-dimensional, smoothly embedded submanifold of our n plus 1. This is the nicest proof that's given in this chapter. He gives a more complicated slice chart proof earlier in the chapter, but oh yeah, this one's nice. Anyway, I think that should suffice for us for chapter 5. Listen, it'd be good for you guys to read it, but I think we're going to go on just because the density of topology in chapter 5 is too much. It's too much. I do have an example. I have an example from another book I wanted to share with you guys. So I may make like a little video of it just because it's kind of, I want to start with the Lie groups next time. I don't want to, but anyway, my apologies for the disjointedness of this material.